Okay, so we are going to continue moving forward with our muscle chapter. You guys picked up a packet last time in class, and this is going to actually carry us through our three discussions of the muscles. So we already talked through the first slide that kind of compared and contrast the different types of muscles that we have. And then we also went through the major parts of the muscles. Today, I'm going to move through the layers of the muscles and the different parts or organelles that we have and do a little bit talking about some of the later material in the packet as well. We are going to completely skip over muscle contractions. I'm going to leave that one for our face-to-face discussion, just because of the material involved there tends to be the area where we have the most new information and things that people are not familiar with. So I would rather do that one on a face-to-face discussion. So within your packet, we should be looking at the slide that talks about the layers of the muscle. And this was something that I had already kind of alluded to, is that the muscle itself is going to be these individual fibers or bundles that are going to then be collectively wrapped together. So this is an alternating system of having fibers and then having a layer of connective tissue bundling it together. And we repeat that process multiple times, ultimately building to the muscle as a whole. So when you look at this particular slide, what it's trying to show you is it's indicating the individual fibers that you have and then how those are going to be wrapped or bundled together and the names of the different connective tissues that are going to be responsible for that bundling process. So when you look at the top, it talks about the muscle coverings. You have the epimysium, you have the perimysium, and the endomysium. And those are going to be the three layers of connective tissue that are going to wrap around the bundles and hold them together. And then you have the fascia, which is going to collectively hold everything together. So that kind of covers the surface of the muscle as a whole. And you can see that on the picture that you have there on the side. The structures that are identified at the bottom half of that slide, starting with the muscle organ, going down to the myofilament, those are all the structures that are being bundled or packaged together. So the top part, the connective tissue, the lower part is looking at the actual structures of the muscle. So I am going to start with this small and work up to the big or to the whole structure of the muscle itself. So when we initially look at it, if you want to look at the thin and the thick filaments that we have within the muscle fiber, when you look at those structures, we have two proteins that are known as actin and myosin. And we're going to spend a lot of time talking about actin and myosin, especially when we get into the muscle contraction. But they are two different types of protein that we have within the muscle structure itself. Actin is a thin protein and myosin is a thicker protein. Because of their differences in thickness, they actually appear to be different colors. Actin being on the thinner side will appear light in color, and myosin being the thicker of the two is going to be dark in color. So when we identified the term striations, I told you guys that your cardiac and your skeletal muscles have this banding pattern to them. And this is where that banding pattern is going to come from. When you put the actin, light in color, next to the myosin, which is dark in color, they alternate back and forth, giving you that banding or that striated appearance. So when you have those two proteins working together, they are going to create a myofilament. Myo, anytime that you guys see that prefix attached to something, it is indicating that you have muscle involved. So those little myofilaments that you guys have are going to be packaged together. And when you bundle a bunch of those filaments together, that is going to take you up to the myofibril level. And if you look at the picture on the right-hand side, you can see those filaments and how you have the individual filaments, and then those are all going to be wrapped or packaged together to ultimately create your myofibril. From there, you have a collection of myofibrils that are going to be packaged together in a group. And when you get a bunch of those myofibrils together, that is going to take you up to the cell status. So when you get a collective group of those myofibrils working together, that is going to create the muscle cell, or what most people would refer to as the muscle fiber. So then the muscle fibers are going to get packaged together in a bundle. And when you get that bundle together, that is going to be what we call a fascicle. And then ultimately putting all the fascicles together is when you get to the largest structure or the overall muscle as a whole. So when you look at the coverings that we have within the muscle, um, and they are identified in the picture on the right-hand side. If you look at it, you can see the epimysium. Right underneath it, you have the perimysium, and then you have the two arrows that are showing where the endomysium is at. So when you look at the endomysium, that is going to be the protective covering that you guys are going to have around your muscle fibers. And if you look at the picture, it's a white area, and you can see how that is going to surround or contain a bunch of those muscle fibers together. So you get those all packaged or wrapped together, and then that is going to create the next level, which is the perimysium. The perimysium is going to wrap around the fascicles, and so it holds all of the fascicles together, and then that ultimately is going to get up to the epimysium, which is going to surround everything. For extra protection, you get the fascia, and the fascia is going to be another protective layer that you have over the surface of the muscle in order to help stabilize it. And then ultimately, you get the tendon, which is going to connect to the bone and hold that muscle in place. We've already touched on the fact that your tendon is actually going to arise out of the muscle tissue. This is not something that is attached or adheres to the surface of the bone or to the surface of the muscle. It actually is going to come out of the fibers and the structures that make up the muscle, as well as that periosteum, which is going to be that skin protective covering that you have over the surface of the bone. This allows for there to be the stability and the strength to hold that muscle in place and hold it to the bone. And you guys can carry out all the different activities that you do on a given day and don't tear that muscle free from the bone. You can tear a muscle. It's difficult to do, but it is possible. And when you do physical activity to the point where a day or two afterwards you have muscle soreness, that muscle soreness can come from a couple of different places. Most of the muscle soreness that we feel is actually going to come from the buildup of lactic acid in our muscle tissue. And then you also have, through physical activity, you can actually tear the muscle fibers. And typically, when we tear muscle fibers, we do just a few strands or individual fibers themselves. We don't tear the entire muscle as a whole. And this is actually how you would build muscle mass. So some of those fibers would become strained and break through physical activity, whether that is lifting or some other type of training. And then in the repair process, and we see this with bones also, when we repair those tissues, we do kind of an extra repair. And so you have more there after the repair process than what was there prior to. So in rebuilding and fixing those muscle fibers, you actually will get more after the process than prior to. And over time, when you do that repeatedly, that is how the muscle mass will ultimately increase in size. If you flip down to the parts of a muscle, so looking at this particular slide, you are starting to look at some of the organelles that you have inside of a muscle cell. And when we talked about a typical body cell, we went through the organelles, and as we talk about this with the muscle, you'll start to see that there's some overlap. So some of the terms and organelles that we had in our other cell types, you'll see a connection here as well. Some of the names are slightly changed, and some of them are brand new just because we're in a completely different type of cell. So the first one identifies the sarcolemma. The sarcolemma is the equivalent of the cell membrane. This is going to be the layer that you have surrounding the entire muscle fiber, holds all the contents together, and regulates what is able to get in and out of the muscle cell. So just what the cell membrane would do for a typical body cell, the sarcolemma does for the muscle. We just refer to it as sarcolemma to indicate that it is a cell membrane found on a muscle. Then we have the sarcoplasm. The sarcoplasm is the equivalent of cytoplasm. And again, sarcoplasm is going to fill any available space that is not taken up by organelles or other structures within the muscle cell. It helps to maintain the shape of the cell. It helps to move material through the cell, has a consistency slightly thicker than water, but just that fluid that is going to fill that available space. Then we have the sarcoplasmic reticulum, which is abbreviated as the SR, the equivalent of the endoplasmic reticulum in a body cell. And we also have the transverse tubule, and I'm going to talk about these together because they work as a group. Now, transverse tubule is a structure that is brand new to the muscle. We did not have a structure like this when we talked about our typical body cell. Now, the sarcoplasmic reticulum is going to be a structure that you guys have that runs over the surface of the cell. And you can see in the picture there, they are these structures that are going to kind of run across the muscle cell. And you also have structures within the sarcoplasmic reticulum that are known as the cisternae. These are going to be holding tanks, essentially. And these holding tanks are going to hold calcium. Now, typically in the body, when we talk about calcium, we associate that with bones. We know that calcium is going to give our bones strength, and that's where we always hear about it in the media, commercials, things like that. The reason that we have to have calcium in our bodies and we have to keep it at a high level is because of our muscles. Your muscles do not contract unless they have access to calcium. So the cisternae are going to hold calcium ions on hand in large volume so that when the impulse comes into a muscle that it needs to contract, those cisternae are going to release that calcium. The calcium floods over the cells in the muscle and causes changes which will ultimately carry out the muscle contraction. Now, that's the discussion we're getting into next week, but just so you kind of have an idea, a little bit of background as to the beginning of that process. So in these cisternae, tons of calcium ions are held, and they are going to work with the transverse tubule or the T-tubule. So you'll notice that the sarcoplasmic reticulum, like I said, runs over the surface of those myofibrils that you have within the muscle. So they are going to help disperse the calcium that way. But you also have to get the calcium to every part of the muscle so that it can carry out the muscle contraction. The transverse tubules, and it's honestly very difficult to see in this particular picture, but the transverse tubules dive down into the muscle. So the sarcoplasmic reticulum kind of runs over the surface, but those transverse tubules are going to cut down and into the muscle so that all of the layers, all the way down through the middle and the core of that muscle, are going to get those calcium ions delivered once they're released from the cisternae. So it's a transport method to get that calcium from where it's initially held to every single fiber in the muscle so that everything is going to eventually contract when the muscle is needed. So sarcoplasmic reticulum holds the calcium, will also deliver the calcium to different parts of the cell. Transverse tubule is going to also deliver calcium. It just takes it in a different direction. So sarcoplasmic reticulum gets more of the surface. Transverse tubule is going to deliver it down to the core structures of the muscle. Myofibril, we already talked about actin and myosin. We will get more into when we talk about the muscle contraction again. Just understanding right now that they are proteins, that they have a difference in their thickness, which also is going to play a role in their overall color. The thin actin appears lighter in color, thick myosin appears darker in color. And then the last term that we have there is called the sarcomere. Sarcomeres are the smallest unit that you have within a muscle. And the best kind of visual that I can give you when you think of a sarcomere is if you have ever taken apart a click pin and inside you have that little spring, that is essentially what a sarcomere is. But when you look at your muscle, you would have those sarcomeres lined up one after another. And kind of like the cars that you have on a train are lined up next to each other, those sarcomeres are lined up end to end in the same fashion. Now, the reason that I compare them to a spring is because if you've ever taken that spring, you guys know that if you grab it, you can pinch it down and make it smaller, and the ends of the spring slide in, which will make the sarco or the spring shorter. When you release the sides, it will slide back to its original length, but it doesn't go past that. It doesn't continue to extend out, it doesn't flatten out. It just slides back to its original size and stays there until you pinch it down again, and then it will get smaller. This is exactly how your muscle contractions work. When a muscle contracts, and we like to use the terms to contract and then lengthen, but what actually happens is the sarcomere will slide down, so the sides come in, making the sarcomere shorter. And when that happens across all of those sarcomeres, which are laid end to end, we see that as a muscle contraction. When the muscle relaxes, the muscle doesn't lengthen, it just slides back to its original size. So all those sarcomeres, just like when you release that spring, it goes back to its original size. Those sarcomeres would slide back to their original size, and that's what we see as a muscle relaxing. Because of this setup, your muscles can only work in one direction. Muscles only pull. And so, again, getting into our conversation for next week, because a muscle can only pull, it has to have what we call an antagonist, which is a muscle that will work in the opposing direction. So when you guys flex your arm and make your bicep flex, in order to get out of that position, your bicep doesn't do anything. So the bicep is not going to be able to push your arm out and extend you back out to a normal position. Now you are going to be dependent on the tricep, the muscle on the opposing side. It actually has to contract to pull your arm back to normal. So like I said, getting into a little bit of our discussion for next week, but kind of laying the foundation for that process. Now, if you will take a little bit of a jump, we're not doing anything with muscle contractions today, but I do want to have you guys go to the slide that indicates origin and insertion. So when we talk about how your muscles work, your muscles are known to work with the bones in order to cause movement within the body. In order for this to happen, where the muscle starts and where the muscle ends has to happen on opposite sides of a joint. So even though your muscle contracts, if it started and ended on the same bone, you wouldn't get that lever type setup and you wouldn't see any movement being carried out in the body. So when we talk about origin, it's identified or defined as being the immovable end, and insertion is referred to as being the movable end. What that means is where your muscle starts, you don't see any movement in that bone of the body. But where the muscle ends or inserts, that is where you would actually see muscle or movement being carried out. So if you think about your bicep, easy one to use, it is going to actually originate on your scapula and the top of the humerus. And then it is going to insert on your radius and your ulna. So it finishes on the two bones of the lower arm. So we're on opposing sides of our elbow joint because it starts above the joint and then it inserts below the joint. So now when your muscle contracts, you guys are going to see the movement being carried out in the lower arm. The humerus doesn't go anywhere. When you contract your bicep, it is the lower arm that is going to move. Nothing happens with the humerus. And that's why we call the origin, or where the muscle starts, the immovable end, because that bone doesn't go anywhere. It is the bones on the opposite side where the muscle finishes, where you would actually see that movement being carried out within the body. And then the last slide, muscles working together. With the number of muscles that we have in the human body, and as I mentioned prior class, we're looking at typically 630 to 640 in the number of muscles that we have in the human body. It is not uncommon that you have muscles that are going to work together in order to carry out a particular movement. So you would have your main muscle that we refer to as being the prime mover, and that is the one that is really doing the load of the work in getting the movement to be carried out within the body. But it is going to need some help and get some assistance from some other muscles in the body. And so we have the terms synergist and antagonist. Synergists are going to help with the movement of the prime mover. They are typically smaller muscles, and so they are going to help control the prime mover and give you a little bit more refined movement. Prime movers, because they carry out most of the movement, tend to be a little bit larger, and they also are going to typically not give you the fine motor skills that you would want to have. So those synergists are going to be a little bit smaller muscles. They're going to allow you to kind of pinpoint and be more on target with your movements than what you would be if you had to rely on the prime mover all by itself. Prime mover also can be referred to as the agonist, carrying out the initial movement. And then you have the antagonist, which is going to be the opposing movement. If you have somebody that antagonizes you, they go against you. Whatever you say, they do just the opposite. And that antagonist muscle is going to do the same. So they are going to make sure that once you've carried out a movement, that if you want to return to your original position, you have the ability to do that. So if you draw your leg back to kick a soccer ball, so the prime mover that would have carried out that particular movement would have been your hamstring. And then when you want to go back to a normal position, you are going to use the quad in order to get you back to your normal position. So you have different muscles that are going to work with each other in order to carry out the different movements of your body. We will talk more about antagonistic pairs and partners as we get into our muscle contraction discussion next week. So look for your assignment tomorrow. It will be posted in Blackboard. And if you have any questions between now and our next class, please let me know.